just did that.
Oh, okay.
Okay, guys, listen. Quiet down. Alright, so the last couple of days we've been going over logarithmic functions and equations and expressions. So we're going to move on today to exponential equations and solving them. So the title of today's notes is Solving Exponential Equations. Okay, so what makes an equation an exponential equation? It's when our variable occurs in the exponent. Okay, so we're first going to look at exponential equations that have the same base. Okay, so if we have b to the power of x equals b to the power of y. What is our base? B. Okay, so they both have a base of b. So they have the same base, then our exponents are equal. Okay, so if b to the power of x equals b to the power of y, we have the same base, then x equals y. Our exponents will equal each other. Okay, so let's look at a few examples of solving with the same base. So we have two exponential expressions equal to each other. They have the same base of what? 7. So we can pretty much get rid of our bases because they're the same base, and we'll just set the exponents equal to each other. Now it becomes a simple equation, and we can solve for x. So what do we do first? Minus 2x. We're left with 1 equals x minus 2. Add 2 to both sides. X equals 3. Alright, so that was really easy, so let's go take it a step further. Okay, here it looks like I don't have the same bases. I have a base of 3 and I have a base of 27.
And 3.
Alright.
27.
Hmm?
Can't 3 go to 27.
Okay, what do you mean by that?
3 is like 3 divided by 27.
Okay, so 27 can be changed to a base of 3, right? 3 to the power of what will give me 27? 3. 3 cubed is 27. So we can rewrite this as 3 to the power of 2x minus 1 equals 3 to the power 3, we still have an exponent of x. Okay, now we have the same basis, and we can set the exponents equal to each other. And solve for x. X equals negative 1. Right, another example. We're going to look at another example just like that. And make sure everybody gets the hang of it.
What is are we gonna have an equation where?
They don't have the same basis and you can't? Yes, we're getting to that. Okay. So example number 3. Okay, how can I make these have the same base? 5 to the power of 2.
So we must start 2.
So we're going to rewrite this as 5 to the power 3x minus 8 equals 5 to the power 2, but I also have a 2x here. Okay. Drop your 5's. 3x minus 8 equals 2 times 2 is 4, so 4x. So we can solve for x. Minus 3x minus 3x. X equals negative 8. Okay, let's look at one more example that's a little bit different than those last two. And then we'll look at different bases. Okay, so this time we have 4 to the power of negative 2x times 4 to the power x equals 64. Okay, the first thing I would do is I notice that on my left side I have two exponential expressions, but they both have the same base. I would combine those two. How do we combine them? What do we do with their exponents? You add them. You add their exponents. Power times a power, so I add. You add the exponent. We're going to have a base of 4 minus 2x plus x equals 64. Okay? Now, how can I make 64 have a base of 4? 4 cubed. So I have 4 and 4 cubed. Okay? So I drop my bases. Get negative 2x plus x equals 3. Okay, let's now combine our x's. Negative 2x plus x is negative x. What's the last step? What's the last step? So we're going to divide by negative 1. X equals negative 3. So that is solving with the same base. Now let's look at different bases. Right, so different bases. There are 3 steps that you need to follow when you're solving with different bases. And they're pretty similar to solving logarithmic functions, or solving logarithmic equations. They're similar to those 3 steps. So step 1, isolate the exponential expression. Step 2, take log or the natural log of both sides. No. Well, it's your preference. It will work with either way. You can use logarithm on both sides, or you can use natural log. Sometimes it works easier to use one or the other. And we'll see examples of that. And then step 3. Solve for your variable. Okay, and because this is a little bit more challenging than just solving with the same base, we're going to do a few more examples than we did with the last one. Okay, so example number 1. Start off simple. 5 to the power of x equals 7.
So we could say log or just the 5 or the concept.
So there's no possible way that I can make 5 and 7 the same base, right? Okay, if there was, then we would skip all those steps and just do what we were doing before, where we would drop the bases and set the exponent equals to each other. However, there's no possible way that I can make 5 and 7 the same base. So, step 1 says to isolate the exponential expression. Which one is my exponential expression? 5 to the power of x. Okay, is it isolated? Is it all by itself?
No.
Yes. Yes, it is. 5 to the power of x is all by itself. There's nothing added to it. Over here, there's nothing multiplied to it. It's already by itself. Okay, so step 1 is done. Step 2, take the log or natural log of both sides. Okay, so we're going to take the log of both sides. Okay? Using our power property from logarithms, where does this x go? It goes to the front. Okay? How do I now solve for x? My last step, solve for your variable. We're going to divide by log 5. So x equals log 7 divided by log 5. And that is approximately 1.2.
Most of these equations with the different bases are running decimals.
About 90% of the time they will be decimal. Okay, let's look at another example. make 3 and 15 have the same base? No. Okay? So I'm going to do the same thing. Is my exponential expression isolated? Yes, it's all by itself. Okay? So we do log of both sides. Okay, what happens to that exponent? Comes out front. Okay, what would I do next? We're going to divide by log 3. Okay, then we'll be left with 2x plus 1 equals log 15 over log 3. Okay, now I need to solve for x. What would I do next? Subtract 1. So I get 2x equals log 15 over log 3 minus 1. And then the last step, divide by 2. Okay, be careful when you put this in your calculator. I suggest that you put the log 15 over log 3 in first, get an answer. Subtract 1, get an answer, and then divide that answer by 2. 0.73 is what you should get. Approximately 0.73. Yes, right.
With the 15, would it be easier to simplify, or that's just pointless?
Simplify what?
The 15 at the beginning of the problem, like 5 squared, 5, like, no. Travel.
Okay, third example. One half to the power of x equals 3. Okay, what would I do first? Take the logarithm of both sides. Okay, what happens to my x? Comes out front. How do I solve for x? Divide by log of 1/2. So that is approximately
Negative 1.5 and 1.6.
so negative 1.6. Alright, so I think we have the hang of that. Everybody feel like they have the hang of it?
Slight.
You want to do one more?
Yeah.
Okay. And then we're going to do that in 2 more examples. So wait. So, let's see, example 4. Do one more. Okay, first step, isolate the question, is it isolated? Yes. Okay, take the log of both sides. Where does that x go? Out front.
You divide by 5.
So divide by log 5, which is approximately
1.6.
1.6. Alright, now let's look at one where it would be easier and also would make sense to use the natural log. So far, all of our examples have had a base where it was a number. Okay? Right? With this example, my base was 5. The previous example before that, my base was 1/2. In this example, my base is still a number, but it's e. Base of e, the natural base. So when we have a natural base, it makes sense to use the natural logarithm.
So will they always use E to show it? Do they always use the letter E to show it?
To show what?
Show change.
The natural base.
Yeah, like they always use that there as well as showing.
Yes, that's what e is. The natural base. It's 20 something. Okay, so first step's already done, it's already isolated, I have e to the power of x, it's all by itself. So step 2, this time instead of taking log of both sides, we're going to take ln of both sides.
Does the x2 go in front?
Well, okay, we can put our x out front just like we were previously doing. However, don't ln and e cancel each other out, sorry. Yes. So that just cancels and I'm left with x equals ln of 30, which is approximately 3.4. And let's look at another one with a base of e.
Is the answer still wrong? It's still in x equals 1. I mean, is the answer wrong if it's in x equals 1? Like x.
If this wasn't here, it'd still be x equals.
I'm saying, because we didn't put 3.4, it says we did.
If you just left it as ln of 30, it's
Take it out.
I don't know.
if you got to that point, probably not. No, I probably would. Alright. Okay, this one's going to require a little bit more work. Still just as easy. Alright, so this time I'm going to need to actually do step 1. Okay, it is not isolated, it's not all by itself. Why is it not all by itself? Because there's 150 multiplied by it out front. So if it's multiplied, what do I need to do to get rid of it? Divide. We need to divide by 150. Then we're going to be left with e to the power 0.05x. 340 over 150 is reduced down to 34 over 15. Okay, now that my exponential expression is all by itself, we can take the natural log of both sides. Okay, ln and e cancel. Okay, how do I get x by itself?
Divide by 4.
divide by 0.05. Again, be careful when you enter this into the calculator. Use your parentheses correctly. So this is approximately
26.04.
Anybody else get anything other than 26?
I got 16.4.
16.4. Okay, that's what I say. Make sure you're typing this into the calculator correctly. The way I would do it is I would say ln of 34 divided by 15, all in 34 over 15 is in parentheses. Get an answer for that and then divide that answer by 0.05. Alright, any questions so far? Alright, let's take it a step further. Alright, this time, so all the ones that we've done so far with, where they had different bases, except for this one, we had to isolate this one, but it was just dividing. So let's look at more where we have to actually isolate. Okay, so this problem I have 4 to the power x plus 2 minus 2 equals 12. How would I isolate my exponential expression? Add 2. You're going to treat this just like a simple equation in order to isolate your expression. Okay, now that my expression is isolated, take the logarithm of both sides. Exponent comes out front. Divide by log 4. Subtract 2. And that is approximately
Yeah, -0.1.
-0.1. Everybody get that? Writing the wrong number. Guys. Okay, we're going to subtract 8. I get 2 e to the power x equals 4. Is it by itself yet? No. Divide by 2.
do you get it?
0.69 or 0.7. The ln button is right below your logarithm button on your calculator.
Shall we got it right? I can't even see the number on
Alright, let's do one more example before I give you your classwork.
And it's not 0.7.
It is 7 when you round it.
0.69.
Alright, so this problem is a bit more challenging.
Oh. What do you like?
Hold on, let everybody write it down first and then we'll go over it. What other type of problem do we see when we have a variable squared, a variable plus a constant?
We see all of them.
Factoring problems, right?
See, I was thinking.
A quadratic equation. We're going to treat this just like a quadratic equation, where we're going to factor this. Okay? Okay, so draw your two sets of parentheses. You're going to have an e to the power x in both. And remember, we're going to treat this just like a quadratic equation. So what are the factors of 3 that when I add them together give me negative 4? Negative 3, negative 1. Okay? So now that I have it factored, I can set each one of these factors equal to 0. Okay? So for the first one, I'm going to add 3 to both sides. Take the ln of both sides. X equals ln of 3, which is approximately
1.0986.
so 1.1, right? Okay, well let's do the second one. Add 1 to both sides, e to the power x equals 1. Take the natural log of both sides.